A power series is a series of a particular form. So power series look like this. Summation n equals 0 to infinity of Cn times x minus a to the n. I think I'm going to use x naught. Okay. So here, two things are given to you. Cn is given and x naught is given. So if n is equal to 0, you get C naught. If n is equal to 1, you get C1 times x minus x naught. If n is equal to 2, you get C2 times x minus x naught squared. See, n is equal to 3, you get, whoop, no, you don't. You get C3 times x minus x naught cubed. And this thing just keeps on going and going. Okay, it's a regular series, but it has a particular form. So here's a couple of examples. Okay, so in the first one, I'm going to let I'm going to let x naught be 0, and I'm going to let Cn equal to 1. So then I get the sum n is equal to 0 to infinity. Cn is 1, and this is for all n. And then I get x minus 0, which is just x to the n power. Okay, and this is 1 plus x squared plus x to the n. Okay, so that, which looks to us like a regular series, is a power series. Okay, number 2. I'm going to let x naught still be 0, but I'm going to let Cn be minus 1 to the n over n factorial. So that's going to give me the sum, n equals 0 to infinity. The Cn is minus 1 over n. Sorry, is minus 1 over n. N factorial x to the n. Now, one thing you need to know for all of the future is that 0 factorial is always equal to 1. Otherwise, mathematics doesn't work. So 0 factorial is not 0. 0 factorial is 1. Okay. So when I put in n is equal to 0, I get 0, 0. So everything's raised to the 0 power over 1. So I get 1. The next term is going to be minus x over 1. The next term is going to be x squared over 2 factorial. The next term will be minus 3. Oh, no, it won't. It'll be minus x cubed over 3 factorial. X to the 4 over 4 factorial plus dot dot. And it again keeps going on forever. Okay, now let's try something a little meatier. Number 3. I'm going to let x naught equal 2, and I'm going to let Cn be 1 over the square root of n. Okay, so now I get the sum, n equals 0 to infinity. Oh, I can't use that one. One over the square root of n plus 1. Okay, so now, oh good. So now I'm going to get x minus 2 to the nth power over the square root of n plus 1. So when n is equal to 0, I'm just going to get 1. When n is equal to 1, I'm going to get x minus 2 over the square root of 2. When n is 2, I'm going to get x minus 2 squared over the square root of 3. When n is 3, I'm going to get x minus 2 cubed over the square root of 4. Okay, so all of these are power series. Now, some power series converge to a number and some don't. And some diverge. Okay, and it's up to us to determine not only if a power series converges, when if it does, when it converges. Okay, so let's look at that first example. So that first example was the sum n equals 0 to infinity of x to the n. Okay, so now this, if you take the sum and you add 1 on the outside and you subtract 1 on the inside, you end up with the same series. Okay, so if you take and you add 1 on the outside and subtract 1 on the inside, you end up with the same series. Okay, so this series, if you recall, has a name. What is that series? Series has a name.
Is it the geometric?
It certainly is. This is a geometric series. And I know when geometric series converges. So if the absolute value of x, which is our r, here r is equal to a is 1, and r is x. So if the absolute value of r, which is the absolute value of x, is less than 1, then this geometric series, the sum n equals 0 to infinity of x to the n, sums to 1 over 1 minus x. How cool is that? Right there, our first function. So the function f of x equal to 1 over 1 minus x has a power series expansion of x to the n. Okay, so that's the power series expansion for 1 over x. One over 1 minus x, I should say. Okay. Let's look at the second one. Oh, I don't remember the second one. I changed my notes. The second one is the sum. Okay, let me just grab it. Okay. So number 2 okay, so this was number 2. Okay, so the question is, when does this power series, I should say where, not when, where does this power series converge? Now, in this section, we will make use of the last 2 tests we learned, which were the ratio test and the root test. And so for us, the easiest one to use is going to be what? What test do I want to use?
The ratio test?
I want to use the ratio test. Why, Lawrence? What gave you the idea to use the ratio test, Lawrence?
I just thought because of the factorial and
That
the
is
denominator.
right. That is exactly right. I'm so glad you answered, because now I know that you are able to provide the answer to the rest of the class. All right, so again, factorials signify the ratio test, okay? If we can use it, go ahead and use it. Okay, so let's look at this. Okay, so in order to do this test, we're going to say that for the ratio test, this whole thing becomes AN. So minus 1 to the n, x to the n over n factorial. Now, if you remember the ratio test, let's just remind ourselves the ratio test on the side of the page. So for the ratio test, we computed rho, which was the limit as n went to infinity of the absolute value of AN plus 1 over AN. And we said when that thing is less than 1, the series converges. Okay, so let's compute rho. So we find out first that AN plus 1 minus 1 to the n plus 1 x to the n plus 1 over n plus 1 factorial. Okay. Maybe I shouldn't have done this one first. It's okay. We'll keep going. Okay. So rho, the limit as n approaches infinity of the absolute value of AN plus 1 over AN. So that's the limit as n approaches infinity of the absolute value. So an plus 1 is minus 1 to the n plus 1 times x to the n plus 1 divided by n plus 1 factorial. And when I divide by an, I multiply by its reciprocal. So I'm going to get n factorial over minus 1 to the n x to the n. All right, now this is why absolute values are absolutely crucial now. This is the limit as n approaches infinity. Okay, so the minus ones are going to be gone because of the absolute value. So I'm going to get the absolute value of x to the n plus 1 over x to the n. And then I'm going to have n factorial. Well, n factorial over n factorial over n plus 1 factorial. Okay, so this is the limit as n approaches infinity. So now this becomes the absolute value of x to the first power, because x to the n over x to the n divides out. It leaves 1x, and that 1x is still stuck inside the absolute value. Then n factorial over n plus 1 factorial gives me 1 over n plus 1. And as I take the limit as n goes to infinity, I get 0, which is less than 1. So what does that say? It says this series converges for all x. Now we can go further and say, since it converges for all x, the interval of, so the radius of convergence is infinity, because it's the entire real line, and the interval of convergence is minus infinity to infinity. Okay, I want to do a different power series. The power series I want to do is the sum n equals 0 to infinity of, oh, well, let me just say, let me stop back first. I'm going to let Cn be minus 1/2 to the n. And I'm going to let x naught be 3. Okay. When I do that, my series becomes the sum n equals 0 to infinity of minus 1/2 to the nth power times x minus 3 to the n. So that's the power series that corresponds to Cn being minus 1/2 to the n and x minus x naught, I'm sorry, x naught being 3. Okay. All right, so now I ask the same question, where does this power series converge? So I need to check, all right? So when I check this, I get an is equal to I'm sorry, guys, I'm having a brain fog. Minus 1/2, oh, nope, is it minus? Yeah, minus 1/2 to the n times x minus 3 to the n. And an plus 1 is minus 1/2 to the n times x minus 3 to the n plus 1 times x minus 3 to the n plus 1. Okay, so rho is the limit as n approaches infinity of the absolute value of an plus 1 over an. So that is the limit as n approaches infinity. So now I'm going to get a true value here. I'm going to get 1/2 to the n plus 1 times x minus 3 to the n plus 1. And then I'm going to get 1/2 to the n times x minus 3 to the n. And all of that is an absolute value. Okay, any questions, guys? Everybody okay? All righty. So the 1/2 to the n plus 1 over the 1/2 to the n just becomes 1/2, and it's already positive. So I'm going to pull it out of the absolute value. And then I'm going to have x minus 3 to the n is going to divide out, and that's going to still leave me an absolute value of x minus 3 inside the absolute value. And in order for this to converge, this must be less than 1 for convergence. Okay. So now I get the absolute value of x minus 3 is less than 2. And this number right here becomes my radius of convergence. Now notice the other one, the radius of convergence was infinity because it always was less than 1. Well, this one, I now am looking at the absolute value of x minus 3 less than 2. So this power series is about x naught equal to 3. So I'm trying to find how far from 3 this thing actually converges. All right, so this is the radius of convergence. Okay, so now we need to find the interval of convergence. All right, so to find the interval of convergence, we have to solve this. So we have the absolute value of x minus 3. Sorry, we don't need absolute values anymore. We get -3. No, we don't. We get -2 is less than the, we don't have absolute value, is less than x minus 3 is less than 2. Okay. And then we add 3 to every piece and we get 1 is less than x is less than 5. That is the interval of convergence. Now, I always call this the preliminary interval of convergence. Because we don't know whether or not this thing converges at 1 or at 5. Okay, so note when x equals when x equals 1, rho is 1. And remember, the test was inconclusive. And at x equal to 5, again, rho is 1, and the test is inconclusive. So the test only tells us the inside of the interval. We still have to check the endpoints. Okay? So you have to check the endpoints. Okay, so I'll show you how to do that on the next example. Because for this example, we don't need to check the endpoints. And the reason why is because this is a geometric series. Okay, so note this power series is a geometric series. So let's see what it looks like. Aha, let's bring it back. So let's take this. This is a geometric series. So I can write this as the sum n equals 0 to infinity of -1/2 to the x minus 3, I'm sorry, times x minus 3, the whole thing to the nth power. All right. So this is a geometric series if r is equal to -1/2 times x minus 3. So we know the absolute value of r has to be less than 1. So the absolute value of -1/2 times x minus 3 has to be less than 1. So we get the same thing again. We get the absolute value of x minus 3 has to be less than 2. So therefore, 1 and 5 are not included. So therefore, our final interval of convergence turns out to be 1 to 5. All right, so the endpoints are not included. Okay, let's look at this power series. What number was that? Was that 2 or 3? That was 3. All right, let's look at another one. Let's look at 4. All right, here's the sum. N equals 0 to infinity of x to the n over n times the square root of n times 3 to the n. Okay, so what is Cn? And what is X naught? Hello? What is C naught? What is Cn and what is X naught? This power series is about X naught equal to. You have to know what the power series is about so you can determine the interval of convergence and the radius of convergence. So this power series is about X naught equal to 0 because it's X minus 0. And Cn is 1 over n, the square root of n, times 3 to the n. Okay. All right, so now this is one where I see that I have a square root. So I would probably be happy, more than likely, I could use the ratio test. I can use the root test. It screams to me the root test. So that's what I'm going to use. All right. All right. So we're going to use the root test. All right, let's remind ourselves of the root test. The root test is we want rho equal to the limit as n approaches infinity of the absolute value of an to the 1 over n. That doesn't look like an n. 1 over n to be less than 1 implies the series converges. Okay. So now what's an? An and an plus 1. Please write that on your paper for me. What is an and an plus 1? Oh, we don't need that. Sorry. We don't need an plus 1. We need an. And then we need the absolute value of an to the 1 over n power. That's what we need. So what is an? It is x to the n over n, the square root of n, times 3 to the n. That's an. All right, which you can write as x to the n over n to the 1/2 power, whoa, times 3 to the n. Everything's positive. So the absolute value of an to the 1 over n is x to the n over n to the 1/2, 3 to the n raised to the 1 over n power. So rho is the limit as n approaches infinity of x to the n over n to the 1/2, 3 to the n, raised to the 1 over n power. That is the limit as n approaches infinity. So I'm going to get x to the n to the 1 over n. So that's that term. Oh, and I do need absolute values because the absolute value of x is in absolute values. Then I'm going to get n to the 1 over n. I'm going to get n to the 1/2 to the 1 over n. And then I'm going to get 3 to the n to the 1 over n. Okay, now let's just on the side realize that n to the 1/2 to the 1 over n is the same as n to the 1 over n to the 1/2 power. Okay. So this is the limit as n approaches infinity. So in the numerator, I get the absolute value of x. In the denominator, I get n to the 1 over n. Then I get n to the 1 over n to the 1/2 power. And then I get 3. And when I take the limit as that goes to infinity, I get the absolute value of x over 3, because we remember that the limit as n goes to infinity of n to the 1 over n is 1. If we forget that, we have problems. Okay, so okay. Oh, I'm sorry, guys. I sprained my foot and it is driving me nuts. Okay. All right, so that's what we get. And we have to force that. That has to be forced to be less than 1. Okay. So that gives us the absolute value of x is less than 3. Ah, there's the radius of convergence. Okay, now we got to do the integral of convergence. And we get -3 is less than x is less than 3. So therefore, this is our preliminary interval of convergence. And the reason why I say it's preliminary, because we still have to check the endpoints. All right, so how do we check the endpoints? So we're going to let x actually be 3. Okay? We're going to let x actually be 3. All right, so when x is actually 3, where's my series? So if we let x actually be 3, then the series becomes the summation n equals 0 to infinity, 3 to the n divided by n, the square root of n, times 3 to the n. Oh, well, how nice is that? 3 to the n divides out. So our series actually equals the summation n equals 0 to, oh Lord, n can't be 0. Scroll back, start all over again, scroll back. I done made a boo-boo. All right, so n has to be 1 here. N cannot be 0. Okay, let's make sure. I think that's the only place I wrote n was 0. Yep, and yep, this is the only other place. Okay. N can't be 0. I just noticed that. N can only be 1. Okay, so this is sum of 1, and I get 1 over, and n times n to the n square root of n is n to the 3/2. Okay, so when x is 3, this is what my series becomes. What do I know about this series? Does that series converge or diverge? Hello? Who said it converges?
I said I said the wrong thing. I thought it was diverge, but
Why did you think it diverged, Victor?
I thought there was a limitation when there was like when n equals 1, but that was my mistake. I didn't know if
Okay, do you recognize the type of series it is?
I said P series.
It is a P series. Good. Okay, so this is a P series. Which converges or diverges for P equal to 3/2. So what does it do? P series converges when? P series converges when?
When is great. I think it was great. It was greater than 1, or it was
Yep. Okay. So this converges. For P greater than 1. So now we know that the series converges at x equals 3. All right, now let's let x equal to -3. So then you get the same series. All right, now I'm going to put in -3. And I'm going to get the sum. N equals 1 to infinity. Oh, I forgot. I still had that 0 there. Of -3 to the n divided by n the square root of n times 3 to the n. And that becomes the sum, n equals 1 to infinity, of minus 1 to the n over n to the 3/2. Okay, now this series, this is an alternating series. Which is an alternating series. And I'm going to take the easy way out. Since the summation of the absolute value of minus 1 to the n over n to the 3/2, which is equal to the summation of 1 over n to the 3/2 converges. This series converges absolutely. And remember, convergent absolutely implies converges. So now I can go back and update my final interval of convergence. I have to include -3 and +3 because the series does converge at those points. Okay, any questions about that?
Dr. Lyon,
Yes.
when it comes to the radius of convergence and the preliminary interval convergence, do you want us to find both when solving a problem
Yes.
if it's present? Okay.
The problem is going to ask you for the radius of convergence, is going to ask you for the interval of convergence. So when you do it, you always want to find, so that's a good question. Okay, so let's do some protocol here. To find the radius of convergence and the interval of convergence. Okay. You start off with the sum, n equals 0 or 1 or whatever it is, of Cn x minus x naught to the n. So when you get the absolute value, so if the absolute value of x minus x naught to the n is less than some, no n, is less than some number r, then r is the radius of convergence. Okay. Then 2, you get negative r is less than x minus x naught is less than r. So x is less than x naught plus r and x naught minus r. This is your preliminary interval of convergence. And then the last part, check your endpoints. Okay, if rho equal to the limit as n approaches infinity of, if you find your rho, either using and you either do the absolute value of an plus 1 over an, or you do the absolute value of an to the 1 over n. But if rho goes to infinity, so this is the ratio test. And here I've used the root test. So if rho goes to infinity, then the series diverges for all x. And your radius of convergence will be 0. If rho goes to 0, then the series converges for all x. And your radius of convergence will be infinity. Okay. All right. Multiplication of power series. We're not even, okay, so actually we can add power series the same way we can add any series. Multiplication of power series is really nasty. It requires a lot of work. Okay. Okay. So you have a of x summation n equals 0 to infinity of some an x minus x naught to the n, or whatever it is, and b of x summation n equals 0 to infinity of bn. Both converge for the absolute value of x less than a common radius of convergence. Then you can take a of x times b of x, and that's the sum n equals 0 to infinity of an times the sum n equals 0 to infinity of bn. Now that's more work than it's worth, because this is what it looks like. This is a naught plus a1 plus a2 times b naught plus b1 plus b2. So therefore this becomes a naught b naught oh This looks like, let me rephrase that. Yeah, this looks like the sum n equals 0 to infinity of Cn. And each Cn looks like A naught Bn plus A1 Bn minus 1 plus A2 Bn minus 2 all the way up to An B naught. All right. And that itself is the sum K. Oh, gosh. Of AK Bn minus K. So that's pretty tough. So for example, I have the sum n equals 0 to infinity of x to the n times the sum n equals 0 to infinity of minus 1 to the n x to the 2n over n factorial. Okay, so just the first term C naught is going to be A naught B naught. So A naught is going to be 1 and B naught is 1. So that's easy. C1 is going to be A naught B1 plus A1 B naught. So A naught is 1 and B1 is minus 1 x squared. And then A1 B naught is 1 and A1 is x. So just the first term is minus x squared plus x. So far, we only did 2 terms of the series. And we know it's 1 plus x minus x squared. Then we need to find C2. That's going to be A2 B naught plus A1 B1 plus A naught BN, B2. So we got to do all that. So multiplying is really tough. What's easier is differentiation. Okay, so differentiation, you can assume that you have some function f of x, and it is the sum n equals 0 to infinity of some Cn times x minus x naught to the n. And that thing converges for the absolute value of x minus x naught less than r. Then you can differentiate it. So f prime of x is equal to the sum n equals 1 to infinity differentiate it. NCN x minus x naught to the n minus 1. F double prime is the sum n equals 1, 2 to infinity of n times n minus 1 x minus x naught to the n minus 2, etc. So remember, we found that f of x equal to 1 over 1 minus x was the sum n equal 0 to infinity of x to the n. We said that power series converged to that if the absolute value of x was less than 1. Well, that means then that minus 1 over 1 minus x squared, which is f prime of x, its power series is the sum n equal 1 to infinity of n times x to the n minus 1. So what does that mean? Well, we said 1 over x, 1 over 1 minus x was 1 plus x squared plus x cubed plus dot, dot, dot. Then you take the derivative, minus 1 over 1 minus x squared. That's just 1 plus 2x plus 3x squared. So I can find the power series of the derivative by knowing the power series of the original function. Okay. Another example. I haven't shown you this yet. Oh, now that hurts. E to the x is the sum n equals 0 to infinity of x to the n over n factorial. So another way of writing e to the x, since e to the x, since the derivative of e to the x prime is just e to the x, that means then that e to the x also equals the sum n equals 1 to infinity of nx to the n minus 1 over n factorial. You can just differentiate the series. Okay. Of course, it works for integration as well, except you have to add a plus c. Okay, so integration of power series. Okay, we're going to again assume f of x equal to the sum n equals 0 to infinity of Cn times x minus x naught to the n converges for the absolute value of x minus x naught less than r. Then the integral of f of x dx is the sum n equals 0 to infinity. Cn stays here, but x minus x naught gets raised to the n plus 1, and then you divide by n plus 1. But you have to add on your plus C. Okay. So if I give you for an example, the first 4 terms of the well, 1, 2, 3, 4, 5 terms of the secant of X. So the secant of X is 1 plus X squared over 2 plus 5X to the 4th over 24 plus 61 over 720 X to the 6 plus 277 over 8,064 X to the 8th plus ... Then the integral of the secant of X, so I can find that the integral of the secant of X dx, which we know is the natural log of the absolute value of the secant of X plus the tangent of X plus C, says just integrate this. So 1 goes to X. I get X cubed over 3, and it's still times the 1/2. I get 5 over 24, but now I get X to the 5th over 5. I get 661 over 720, but now I get X to the 7th over 7. I get 277 over 8,064. And that integrates to X to the 9th over 9 plus ... So I found a power series for secant log of secant X tangent X. So that is equal to X cubed over X plus X cubed over 6 plus X to the 5th over 24 plus 61 over 5,040 times X to the 7th. And this crazy number, 277 over 72,576 X to the 9th plus ... Okay, guys, that is it for today. So have a great weekend.
Bye.